Turns out there are going to be two ways we're going to get the mass of the KClO3. To get the mass of the unknown, we just weigh the sample. Two ways to determine in this experiment. Let's talk about the first. It turns out when we heat KClO3, solid, in the presence of MnO2. MnO2 is a catalyst. What catalysts do is they just speed up the reaction, but they don't actually participate in the reaction. That is, they aren't consumed as a reactant. They do participate in that they speed it up. What they speed up is the decomposition of KClO3 to KCl solid plus 3/2 O2 gas. What type of reaction is this? Is that a metathesis, acid base, or redox? Can you determine? So what kind of reaction is that? It's hard to see. Use some pen here. KClO3 solid goes to KCl solid plus 3/2 O2 gas. What kind of reaction is that? How can you tell? Well, is it metathesis? It's not metathesis. Why? As metathesis, you have to have ions, and you're looking for ion combinations. Although KClO3 consists of potassium ions and ClO3 minus ions, KClO2 doesn't. O2 is not an ionic compound. Is it an acid base? No. I mean, is there a proton donor and proton? It might be a Lewis. But how you can tell, sometimes it's difficult to tell if it's a Lewis acid base or redox. But there's one easy way to determine, and that easy way to determine is to look at the oxidation states. So did the oxidation states change? We can just take a quick look at the oxidation states here. Potassium's +1, oxygen's -2, -6, and chlorine's +5. What's chlorine over here? Well, we know potassium's +1, that makes chlorine's -1 and oxygen's 0. So this is a redox. It's a redox because oxygen went from -2 to 0. Chlorine went from +5 to -1. In fact, chlorine, if you go from +5 to -1, how many electrons did you just gain? Each chlorine atom just gained how many electrons? So +5 to -1 gained how many electrons? 6 electrons. And so there are a lot of electrons around. But where do those electrons come from? The oxygen. And so do you see potassium chlorate is what we call both the oxidizer and the reducer. It turns out, remember I kept saying that oxygen's happy, right? Oxygen's happy as is. But in this particular reaction, if we heat it up, maybe, that chlorine is very unhappy. And so that chlorine attacks the oxygen, which is bonded to it, takes the electrons from it. if chlorate could find easier electrons to take, like sugar, remember the potassium chlorate with sugar reaction? That's called the sugar rocket engine or rocket. But anyway, if chlorine can take it from easier sources, it will. But in this case, there's no easier source, and this is both the oxidizer and the reducer, which means that potassium chlorate, is that a stable compound? No, it's not terribly stable, right? And so it's something that is potentially reactive. This is going to, what is KCl? What would you call that? The reducer or the oxidizer? This is a reducer. And oxygen? And so we must be going from stronger to weaker, otherwise there would be no reaction happening. So there is a driving force for this reaction here. And so we're going to just decompose the KClO3. We're going to end up with KCl solid and O2. So method one, we're going to do this all together. But method one is this. Here we're going to have the sample, in other words, the unknown, and MnO2. Then we're going to heat it. The symbol for heat is this little triangle here. When we heat it, then what do we lose? Well, the KClO3 solid is converted into KCl solid. The KCl solid stays, remains in the test tube. We don't lose that. However, does the O2 remain? No, the O2, actually we're going to lose the O2. The O2 is going to escape as a gas. And so we cool this down, and then all we're left with is the product residue. So if we have the product residue, then the difference is the mass before reaction minus the mass after reaction is going to be different. And the difference is going to be due to the oxygen. There's going to be no more oxygen in the solid. All the oxygen was converted into gas and escaped. And so the mass of the oxygen we can calculate. The mass of the O2 gas that was generated is equal to the mass of the product residue minus the mass of the reactant mixture. That is before and after. So final mass minus initial. But the initial mass, we're taking so many masses, we have to be careful. Okay, if we know the mass of the O2, then we can figure out how many moles of O2. And all that O2 came from the KClO3, so if we go moles of O2 to moles of KClO3, we have it. And so this is the stoichiometry we do. So method one is we start off with the mass of O2, convert that into moles of O2. For moles of O2, we'll convert that into moles of KClO3. Because from the balanced equation, the mole ratio is for every 2 moles of KClO3, we have 3 moles of O2. And so for every 2 moles of KClO3, we have 3 moles of O2 generated. So this is the mole ratio from the balanced chemical equation. And from the moles of KClO3, we can go to the mass of KClO3. From the mass of KClO3, we'll just plug that into this equation and solve for what the percent KClO3 in the unknown is. That's the easy way. That's the easy way of doing it. You just have to burn off all the O2. You know, this is our sample here. And then we're done. Make sure there's no more O2 generated and just reweigh it.
Well, that's too easy. We have to do it the hard way, too. The hard way is good because we can get practice with gases. And the hard way is this. The hard way is we are not going to let this O2 escape into the lab. You know what we're going to do? All the O2 that's generated, we're going to capture it. And then if we can figure out the pressure of the O2, the volume of the O2, and the temperature of the O2, then we can calculate the moles of O2. Once we get the moles of O2 from the pressure, volume, and temperature, then we can calculate the moles of KClO3, and then we can calculate the mass of KClO3. Okay? And so we're going to determine how much O2 is generated by two ways. One, by just difference in mass, and then two, by capturing the O2 and measuring its properties: pressure, volume, and temperature. And so how do we capture the O2? Well, capturing the O2 is kind of tricky, but it's standard procedure. If your gas does not dissolve in water, if your gas does not dissolve in water, then we can capture it over water, over liquid water, and that's common. And so this is what we're going to do here for our experiment. I have my unknown here. Where are two of my dogs? And then you're going to work in pairs for this. The amount of unknown they give you is more than you need. Don't use the entire sample. If you use the entire sample, you're going to generate too much O2. The problem with generating too much O2 is our flask has a limited volume. And if you generate more than the flask can contain, then we don't know how much O2 we generated because it'll overflow. And so use the amount that they say to use. Okay, so we're going to need the masses of everything. We'll need the mass of the empty test tube. Remember about fingerprints? Do you guys know about fingerprints?
It adds to the weight.
It'll add to the weight. And so wipe off your fingerprints. Okay, so what I do is this. Our weighing procedure is all convoluted. It's convoluted because of the type of balance. This procedure is written for your basic setup, but we have very expensive balances. With these very expensive balances, you can tear a beaker. For cheap balances, you can't tear a beaker. It weighs too much. And so these balances here are like $15,000. So what we do is we'll just tear the beaker and then put the test tube in the beaker. This procedure is written for the cheapest equipment you can get. Cheapest equipment you can get is a real balance. These balances that look like seesaws? And so what they're saying is get a piece of copper wire and hang the test tube on one end of the seesaw and then put masses on the other end until it balances out. Do you want to do that? No. And so we have to modify our procedure for our balances. Which is okay because, like I said before, modification happens all the time in labs. You modify the procedure depending on how things are going, and we just don't stick. We have to be flexible in that way. So anyway, the easiest way to weigh this is just to zero a beaker and then place the test tube in here. We need to know what the mass of the test tube is. And then you would think, boy, if I want to weigh out a sample, I'd just re-zero this. But don't re-zero it. We need the weight of everything. And so what we're going to do is we're going to tap in our sample and get the total mass. We want the mass of the test tube plus the sample. Okay. But we also have to add some stuff to this sample, and that is catalyst. The catalyst, what you're going to do is you're just going to get a spatula and take about a match head's worth of catalyst and then dump it in there. This doesn't have to be precisely metered out. You just get a match head's worth, dump it in there, and then read the mass precisely. We want to know exactly how much catalyst is in there. But, you know, you could dump in lots or you could dump in a little bit. All you need is a little bit. If you dump in lots, well, no damage done. You just wasted catalyst, that's all. Okay, so what we should have is we should have the mass of the empty test tube, the mass of the empty test tube plus our unknown, the mass of the empty test tube plus our unknown plus the catalyst, and then we're good. If we have those masses, then we can start the experiment. So setting up the apparatus, you're going to work with a partner for this. Setting up the apparatus, we have to heat the test tube. We're going to heat it with a Bunsen burner. If we're going to heat it with a Bunsen burner, you want to make sure that you clamp it. Where should I clamp it? Should I clamp this at the bottom of the test tube? No, because you're going to stink up the lab. This has rubber insulation on here. When this gets hot, it's going to start to smoke and it's going to smell bad. If you clamp it at the bottom, it's going to stink up the lab. So make sure you clamp it at the top where it's going to be a little cooler here. And then usually what we do with these clamps here is I just pinch it and then tighten the wing nut. And so just pinch here and then tighten the wing nut. You should be good. All right, when we heat this, we don't want it vertical. We want to point it at an angle, let's say a 45-degree angle. There's a lock nut here, and what you do is you just screw it until the lock nut is securely against the, I guess, bottom or the back of the clamp here. And so now it's secure at this angle. So you just set everything up like this. Now this is a little high. This is probably too high to reach because I need this. Let's see. Actually, I don't think I need to record this. I'm not going to record this.